Welcome to the Digital Signal Processing Lab. And in this video, we are going to conduct another experiment. And the objective of this experiment is to design a linear phase finite impulse response low pass filter. So here we design the low pass filter, FIR low pass filter using the MATLAB tool. So here you can see before going on to the MATLAB software, we first look at some of the mathematical definitions that will be required, okay, to understand the coding, okay, that we are going to do over the MATLAB. So here you can see this is the ideal low pass filter response, okay, frequency response of the ideal low pass filter. So it will be having a certain pass band in the frequency ranges from 0 to omega c. And after that, we are going to have the stop band. So in this particular pass band, the signal will be passed through the filter without any attenuation. And after that, there will be a completely separation of the signal will take place. So the signal will be completely attenuated in the stop band. Okay. So this particular ideal low pass filter frequency response can be mathematically represented by this particular equation. Here you can see this HLEJ omega, which is equals to 1 within the pass band, omega within this pass band, okay, where the cutoff frequency is equals to omega c, and within the stop band, this is going to be 0, right? So if you calculate the impulse response or unit sample response of this particular ideal low pass filter, then obviously you can do it by evaluating this particular integration, right? Which is nothing but your inverse discrete time Fourier transform definition, right? So just to substitute this value, HL EJ omega equals to 1 into this particular equation. And then if you evaluate this integration, you will be able to show that this will be giving you result equals to sine omega Cn divided by pi n, which is nothing but your sinc function. So if you plot this impulse response of this ideal low pass filter, then you will be find that this will look like this particular signal. So here I have just plotted this impulse response HLPN, okay, which is your sinc function. So this sinc function will extend up to infinity. So this will be nothing but your infinite impulse response. Here you can see that this will be having the infinite impulse response, right? So normally here you can see that see this in this particular impulse response of the ideal low pass filter. It is having obviously it is having the infinite impulse response. And one more thing that you can note down is that this particular impulse response is also exist for n less than 0, right? And because it is also exist for the n less than 0, this is actually your non-causal impulse response, right? So now if you also add the linear phase response within this ideal low pass filter, then this frequency response of the linear phase ideal low pass filter will be represented by this particular equation. So here this HLP E j omega will be given by e to the power minus j omega m by 2 within the passband of your filter. And this capital M by 2 is the it is the delay provided by your filter, right? So it will be a certain sample delay, right? So it will be the m by 2 number of samples delay will be provided by this particular filter, right? So if you take this impulse response, if you take this frequency response, then you can again you can evaluate what will be the impulse response of linear phase ideal low pass filter. Okay, so again you have to calculate the same inverse discrete time Fourier transform by evaluating this particular integration. Okay, so if you do this simple analysis, you will find that the impulse response for a linear phase ideal low pass filter is going to be sine omega c n minus m by 2 divided by pi n minus m by 2. So this will be the ideal low pass filter, linear phase filter. Okay, linear phase ideal low pass filter impulse response. So if you want to plot this, again it is going to be a similar kind of impulse response, but it will be shifted by m by 2 sample towards the right hand side. So this entire response is going to be shifted right hand side by m by 2 sample, right? Because it is providing the sample delay. Okay, it will be m by 2 samples delay within this particular impulse response, right? So it will be just getting shifted by right hand side. Okay, So again, it is an infinite impulse response because it will be extending from minus infinity to plus infinity. So now we have to make it a finite impulse response by just truncating the negative part. Okay. So we have to completely truncate the negative part so that it will become the causal frequency response. And again, we have to make it finite by multiplying it with the particular window, which is having the finite length. Okay. So what we can do is we can have the impulse response of a linear phase FIR filter, okay? Because here it is an IIR filter, okay? So if you wish to get the linear phase FIR low pass filter, in that case, what we can do is we can get this impulse response by just having this impulse response HLPN, and we have to multiply a particular appropriate window function WN, okay? So let us suppose this window function WN, which is finite in length, okay? If it is a rectangular window, in that case, this Wn is going to be equals to 1 for n equals to 0 to m, and otherwise this value is going to be 0. So if you multiply this window function with this particular impulse response of linear phase ideal low pass filter, in that case, we are going to truncate the negative part, and we are also going to truncate the values which is greater than for the n values which is greater than m. Okay, so for all values of n which is outside this range 0 to m is going to be multiplied with 0, and therefore it will be getting truncated. Okay, and therefore we are going to get the impulse response of a linear phase FIR low pass filter, right? So here you remember that whenever we are choosing this window function Wn, this particular window function Wn is following this particular property. And what is this property? Wn is equals to Wm minus capital M minus n. So it means that this particular window Wn, which is we are going to multiply with this particular impulse response of linear phase ideal low pass filter, is actually symmetrical around n equals to m by 2. So it will be a symmetrical window, right? You remember we are generating a symmetrical window, and that symmetrical window will be symmetrical around n equals to m by 2 point, okay? And then it is going to be multiplied with this particular impulse response. So ultimately, the impulse response of your FIR linear phase low pass filter is going to be Hn equals to sine omega c n minus m by 2 divided by pi into n minus m by 2 multiplied with the Wn. So now you can see if we wish to calculate the frequency response of your linear phase FIR low pass filter. So normally what happens is the frequency response of FIR low pass filter will look like something this particular picture. Okay, so normally this dotted line is showing you the ideal low pass filter response, but normally in the practical cases when we design the FIR filter, okay, this kind of ideal responses will not be achieved. So basically, we are going to have a certain pass band, and within the pass band, this gain is going to be fluctuating a little bit, right? So it is not a flat response normally. It is going to be a fluctuation. This fluctuation may be very small, but there will be a certain fluctuation within the pass band. And then this in this case here, you can see in the ideal case, there is no transition band. Okay, it is directly up to omega c, it was passing the signal, and after this omega c it is certainly attenuating the signal. Okay, but in the case of practical FIR filter response, you will find that there is a transition band from omega p to omega s. So what is omega p? Omega p is the pass band edge frequency. So this that particular values are more clearer into this picture, particular picture. Here you can see we are having this pass band, okay, and within this pass band frequency is being defined as omega p, which is nothing but your pass band edge frequency. And then again, we are having the stop band edge frequency here. And in between, we are having a particular transition band. So this is your transition band that you can see, okay? So this gain, which is very high in the normally in the pass band, okay, will gradually decreasing, right? So there will be no steep decrease in the gain you will find, but there is a gradual decrease in the gain of the filter you will find. Okay, so gradually this gain is getting decreased, and then up to pass band, up to a certain value of stop band, okay, this gain has to decrease into a particular allowable range. Okay, So whatever be the your FIR filter specification, that specification we have to follow, right? So it has to means its gain has to be reduced by a certain factor. Otherwise, your FIR filter specification will not meet. Okay. So normally here you can see that again within the stop band, this attenuation is not means the gain is not zero. Okay, that you have to remember, right? There is a certain gain within this stop band also, because there is a certain ripple, but still we are going to get a certain gain within this stop band also, right? So this kind of frequency response we are expected to get when we are designing a practical linear phase finite impulse response low pass filters. Okay, so here you have to remember this certain terms, because there is a ripple within the pass band and there will be a ripple within the stop band. If suppose that we have the maximum absolute gain that might be equals to 1 if it is a flat response, then that flat response may fluctuate, and in this fluctuation we it may go from 1 to 1 plus delta p, and it may also go to 1 minus delta p. Okay, so there must be a fluctuation kind of thing, right? So similarly, a fluctuation within the stop band also will be observed, and let us say this gain, absolute gain within this stop band is equals to delta S, right? So ideally, you remember within the stop band, we don't require any gain. Okay, we don't require any pass band, stop band gain. Okay, and any absolute gain is not required. So this delta S should be as minimum as possible, right? It should be very minimum value. If it is zero, then it is well and good. Otherwise, if it is having a certain value, it means that means it is this response is not like your ideal response. Okay, so that we have to take care. So here you can normally you will find that in the books it is mentioned generally this ripple factor delta p and this delta s both are almost equal. Okay, so if this delta p is, let us say, if it is 0.01 or 0.1, then this delta s is also around 0.1. Okay, so these values are normally equal. Okay, so here we will be taking a certain examples to understand this problem. Okay, so here you can see within the passband ripple. Okay, this is called as the passband ripple or deviation in dB. So that can be calculated by calculating this particular equation. Okay, 20 log 10 1 minus delta p, right? So that will be calculated within the passband. What will be the minimum gain, right? Similarly, here we have to calculate within the stop band. Okay, what will be the minimum attenuation that we are going to get. So that can be calculated by alpha s equals to 20 log delta s. Okay, so that way we can calculate what will be the gain within this stop band and what will be the gain in the pass band, right? So normally for the low pass filter, obviously this gain within the pass band should be high, and within the stop band it should be very small value. Similarly, you can also calculate the transition width by just having this equation. Here is the stop band, here is the pass band. So just you subtract this pass band from the stop band, you will be able to get this transition width. So normally in the ideal low pass filter, this transition width is equals to 0. But in the practical filters, we are not having that characteristics. So there will be a certain transition width, right? So we are going to get a certain transition width. So now, if suppose we want to design a filter, okay, let us suppose we want to design a FIR linear phase low pass filter to meet the following specifications. So what are the specifications? So this filter is having its frequency response, okay, within its pass band. Okay, so here is the pass band frequency mentioned. It is from 0 to 0.19 pi. Okay, so within this pass band, the gain which is available that should be available within the pass band is varying from 0.99 to 1.01. So this is the range. Okay, 1.01, this is the maximum gain, and this is the minimum gain should be 0.99. So these are the absolute gain, you remember, right? So within the pass band up to 0.19 pi, okay, this absolute gain should not drop less than 0.99. This is the requirement that you remember. Okay, so that is the requirement. It should not drop below 0.99. So this is the specification mentioned. Similarly, what is mentioned for the stop band is, so a stop band is lying somewhere in 0.21 pi to pi. So this is our stop band, right? And within the stop band, this absolute gain should be less than or equals to 0.01. Okay, so this gain within this stop band should be less than or equals to 0.01. So the maximum gain which is possible within the stop band is equals to 0.01. So it should not be greater than this value, that you remember. So here you remember that while designing the FIR filter using the MATLAB tool, what we have to perform is uh, we have to we have to try to meet this specification of the filter, right? So while designing here, you can just correlate all these values because omega p is 0.19 pi and omega s is 0.21 pi. And here you can calculate what is the minimum stop band attenuation, or it can also be called as maximum gain in stop band, right? So that we can calculate in dB, and this value, if you calculate, it is denoted by alpha s. So it is 20 log 10 delta s. Okay, here you remember it is log base 10, right? So 20 log base 10 delta s. So here the value of the delta s is mentioned is 0.01. Okay, so if you put this value is coming out to be minus 40 dB. So now this value is coming out as minus 40 dB. So now we have to design a filter, FIR linear phase filter. So now we have to think about which particular window will be offering us this minimum stop band attenuation, which is equals to minus 40 dB. So to understand, I have included one table. Okay, so just you try to see this table. So here are the different windows, right? Rectangular window, Hanning window, Hamming window, Blackman window. Okay. So here you have to just see this table, and here you can find out these are the minimum stop band attenuation offered by these windows, right? So the minimum attenuation offered by the rectangular window is minus 21 dB. Here Hanning window is offering minus 44 dB, then it is minus 53 dB, and here it is minus 74 dB. So different windows are having different minimum stop band attenuation, right? So here you can see, because in this filter the specification which is mentioned, okay, because minimum stop band attenuation required is minus 40 dB. So we can only choose either Hanning window, Hamming window, or Blackman window, because because this filter specification says this frequency response, okay, this absolute magnitude of the frequency response should be less than or equal to 0.01. So this attenuation should be either minus 40 dB or it is more than minus 40 dB, means it could be minus 50 dB or minus 60 dB and so on, right? So this can only be achieved if we choose either Hanning window, Hamming window, or Blackman window, because these values are more than minus 40 dB. Okay, so therefore we can choose only these window. We cannot use rectangular window while designing the FIR filter to meet this specification, because the filter specification that we are going to get will be worse. Okay, so we can have the better filter specification. Whatever it is given, we can design a over meeting specification, but we should not design any under meeting specifications, right? So here we have to choose this three windows. Either these three windows will be suitable, right, for our designing. So suppose if we are choosing the Hanning window, okay, here you can again see this the transition width offered by the different filters are also different. Okay, so it is mentioned over here. You can see it is depending on the it is inversely related with the order of your filter, right? So here M denotes you the order of the filter. So if you choose this Hanning window, okay, then what we can do is first we can calculate the transition width. So transition width is omega s minus omega p. Just you try to substitute this value, you will be able to find out this delta f transition width is equals to 0.01. So now you can just use this formula delta f is equals to 0.9 m, but because I am choosing Hanning window here for designing, so this delta f will be equals to 3.1 divided by capital M. So just to follow this particular equation, you will be able to find out this order of the filter for Hanning window is coming out to be equals to 310. So here we can also define one more parameter which is required in the MATLAB is cutoff frequency, right? So normally the cutoff frequency that we are going to design, we are going to get here is, it is the midpoint of your transition band. Okay, so normally it is the mid point, right? So it should be calculated as omega s plus omega p divided by 2 equals to, if you substitute these values 0.19 pi and 0.21 pi, this value will come out as 0.2 pi. So these are the certain calculation that I did here. Okay, the same we have to implement onto the MATLAB software, right? So now let's move on to the MATLAB software and we'll try to implement the same equations. Okay, I have already written certain codes that you can see here. So you remember in the MATLAB what we have to do is we have to input all these values. Okay, we have to input the pass band edge frequency, stop band edge frequency. Then we have to choose this delta S value. Okay, enter allowed stop band ripple. Okay, so this delta S value. Then I have just done all those calculation, whatever I have shown over there. So okay, so that you can correlate here. Okay, we have calculated delta F, we have calculated minimum stop band attenuation. Okay, and then I have also calculated the cutoff frequency. Okay, and then I have written certain codes to include the different windows, right? So I have just taken all the windows, okay, based on the appropriate choice, okay, based on this minimum stop and attenuation, appropriate filter will be chosen based on this code, okay, that you can try to see and try to understand, right? So here we have to give our choice and then a certain window is going to be selected, okay? So this way we have to first select the particular window and then the window will be going to be generated. Okay, here I have generated the different windows based on our choice. Okay, so here I have generated the rectangular window, Hanning window, okay, Hamming window, Blackman window. Okay, so based on our choice, one of the window is going to be generated. Okay, and it will be stored in the variable win. Okay, I have just made one variable win, and here this window this window generated window is going to be stored. Okay, so those samples will be stored in the variable win. Now we have to generate the time domain waveform of the window and its frequency response. So for that purpose, I have just created this array for time index n, which is varying from 1 up to n plus 1, right? So here I have to get the frequency response of the window. So I have already discussed about the frequency command in my previous lectures. So please go through it and try to understand this freqz command will be used for calculating the frequency response of the window. Okay, the corresponding frequency response and its corresponding frequencies is going to be stored in this variable W1, and the corresponding frequency response is going to be stored in frequency this particular variable FRQ WR. Okay, so now this is going to be plotted. Okay, so we have to plot this frequency response, and you remember while plotting the frequency response, we are normalizing the frequency value. Okay, it will be normalized by pi. Okay, so we have to divide the frequency by pi. And then we have to evaluate this 20 log 10 and then absolute value of this frequency response, and then we have to plot it. Okay. So similarly, I have plotted the time domain waveform of the generated window by using this subplot function. Here again, I have what I did is I have generated this impulse response of your ideal linear phase filter, right? So this equation I have written, okay, sine pi omega c n minus m by 2 into divided by pi n minus m by 2. So this is your ideal impulse response of your linear phase filter that I have already described in the slides. Okay, and then this is the our desired filter. FIR filter impulse response. Okay, so what I did is I have just multiplied this particular impulse response with the generated window, and then I have plotted this values again, right? And later on, what I did is I have just taken this signals, and then what I did is I have actually calculated the filter response. First, what we have to design, we have to design the filter. Okay, so I have used this command FIR1. Okay, so here you see this is the FIR1 command, which is used to generate the filter coefficients, right? So this FIR1 filter, FIR1 command, here, what are the inputs that you can see? So the first input is the order of the filter, M, okay, and the second input is its cutoff frequency. You remember this is not your 3 dB, it is not 3 dB cutoff frequency, okay. So here the cutoff frequency WC is being defined, but at this cutoff frequency, the gain offered by the filter is normally minus 6 dB, okay. And here we have to give which particular window you are using for making this FIR filter, right? So that window we have to give. So there are total 3 input parameters that we have to give to use this particular FIR1 command, and that will be going to return you the filter coefficient value in vector or variable b, right? So now this variable b will be used, and this variable b for this particular variable b, we have to calculate its frequency response. And then this frequency response I have plotted again. And this is going to be our design filter. So now you try to first see there is a new command FIR1 that I'm going to use here. So I'm just introducing this particular command. So what we can do is you can write onto the this particular command window, you can type help FIR1. If you type FIR1 here, you will find its description, right? So here you can see what is FIR1 filter does. This particular command does. Okay, so here you can see this definition of FIR1. It is FIR filter design using the window method, right? So if you write this command b equals to FIR1 n comma wn. So what is this capital N? This capital N denotes you the order of the filter, right? It is nth order of the filter, right? So it is denoting you the order of low pass FIR digital filter. And what is this WN? WN denotes you the cutoff frequency of the filter. So normally this cutoff frequency must be in between 0 to 1. So you remember, because we are talking about the normalized frequency, right? So it will be divided by pi. Therefore, this value is coming out 0 to 1. Otherwise, this value will be in between 0 to pi, because we are talking about the normalized frequency. Therefore, this value is going to be divided by pi. So it must be, you must remember that this all the frequency component here that we are going to input is going to be normalized by pi. Okay, it is going to be divided by pi. Okay, so that way we have to enter the values, right? So here you can see the normalized gain of the filter. Normalized gain of the filter at WN is minus 6 dB. Okay, so you remember at cutoff frequency, whatever we are going to get at that particular point, the gain offered should be around minus 6 dB, right? So here, if you don't give the window, then automatically it will be taking the rectangular window for designing. Otherwise, you can give this window name, okay, which window you want to choose, right? So you can specifically write the windows. Here you can again see this the same command. This FIR1 can also be used for designing the high pass filter, band pass filter, and so on, right? So appropriately choosing this particular command, you can design any filter. Okay, any filter you can design. So I am just using this particular command FIR1 n comma wn comma when. Okay, so that you can look at this description and you will be able to understand. So now try to execute the code that I have written there. Okay, and then we'll try to input those parameters that we have seen in the example. Okay, so let's try to execute this code. Okay, so if we execute this code, okay, so here it is asking you to enter the pass band edge frequency WP. So here in the code, here in the example, if you see what we did is in the example, we have taken this omega p is 0.19 pi, omega s is 0.21 pi. So we have to just take the normalized value. So just to divide it by the pi, and then you input this parameter. So now we have to just input this parameter. So I will make it 0.19. Okay, then WS is 0.21, and then it is asking you enter allowed stop band ripple. So that stop band ripple is 0.01. Okay, so here you can see it is 0.01, right? So this is the stop band ripple 0.01, right? So that we have to enter. Fine. So now if you enter, it will be calculating all those parameters that I have already shown you. So here is the minimum stop band attenuation in dB alpha s. Okay, it is coming out to be minus 40 dB, right? So now because this minimum stop band attenuation is coming out to be minus 40 dB, we have to choose the appropriate window, right? So here, because I have shown you this particular table, okay, so I told you that we cannot choose rectangular window. We can choose either Henning window, Hamming window, or Blackman window, because all this window is going to give you the particular specifications, right? This particular specification will be met or over met, okay? If you choose rectangular window, then this specification will be under meeting, okay? So that we can check it out here. So let us suppose if we first case, if we choose Henning window, right? So you just write, you just give your choice equals to 2, right? So if you write 2 here, okay, it will be taking Henning window, and it has calculated the order of the filter, which is equals to 310, and the cutoff frequency, the normalized cutoff frequency is coming out to be 0.2. Now, if you see this calculation I have already done here, okay, this is the order of the filter is 310 and this cutoff frequency is 0.2 pi. So because there I am talking about the normalized cutoff frequency, it will be divided by pi. So I'm going to get this value is equals to 0.2. So now if you see this results, okay, you see this first result. So this is the window, okay. First here you can see this picture. So here in the top panel, the first figure, okay. So this figure here denotes you the generated Hanning window, okay. And I told you that this Hanning window is normally symmetrical about a certain point m by 2, okay. So here because the window length is of 310 samples, so around 155, okay, this window is going to be symmetrical, right? So around this particular sample value, this window is going to be symmetrical, right? Because this window is started from sample index n equals to 1. So this is the 155th samples, you remember. So around this sample, this is going to be symmetrical Hanning window that we have generated. Now here you can see this is the impulse response, okay, of your linear phase ideal low pass filter. So here you can see this particular equation that I wrote. Okay. So here this particular equation I have generated. Okay. HLPN sine omega c n minus m by 2 divided by pi n minus m by 2. Okay. So that response I'm showing up here. Okay. So this is the response. Okay. You remember one point that is very important here. Although I have just taken the finite number of samples, okay, but you remember while plotting this particular impulse response, this impulse response must be extended up to minus infinity this side and it should go up to plus infinity this side. But I have just taken the finite number of samples and therefore this kind of impulse response I have got. Okay. Now, if we multiply these two functions, right? If we multiply this window with this particular impulse response, you are going to get this particular impulse response. You see, HN, okay? So it is HLPN multiplied with the window function, right? So if you do this multiplication, we are going to get this HN. So here, this particular third graph is actually showing the HN, okay? So you might be confused that both these curves, why it is looks to be same, okay? So you remember, although it looks to be same, but it's if you compare these each sample points, you will find that the values of the sample points are different because it is going to be multiplied with the corresponding value at this particular samples. Okay, so therefore you will find that these values are not same. Okay, you just try to check it out one of them. Okay, so here you can see 151 samples is its magnitude is 0.4677. Okay. Similarly, if you try to see this value, okay, this value's magnitude is different, 0.46656, okay, because it is getting multiplied with this window function and therefore its amplitude is going to be modified, okay. So these are the different waveforms that you can understand. Window, then it is impulse response of your linear phase low pass filter, and this is the impulse response of your FIR linear phase filter. Okay. So now we have generated this all time domain waveform. Now here you can see this frequency response of your window. Okay, this is the Hanning window frequency response. Okay, and I have already talked about the frequency response of your all the different kind of windows in my previous lecture. Okay, so that you can check it out and then you can understand this particular picture, right? So now we have to see the frequency response of our design filter, right? So here is the frequency response of our design filter. This is the frequency response. This is our design filter, designed FIR filter. So here you can just check it out. These values in the pass band, this response is almost flat. Okay, it is almost flat. Very small fluctuation you will observe, but it is almost flat, right? So here you can see there is a fluctuation in the magnitude y. Okay, so here you can see, but that magnitude is very small, right? So there is a very small fluctuation. And now you can see at the cutoff frequency omega c. Okay, so omega c is coming out to be 0.2. So here you can see this value is coming out 0.201. So at this point, this magnitude is coming out minus 7.7. So if you exactly control the value of omega at 0.2, this amplitude, this magnitude is going to be minus 6 dB. That you can check it out. Okay. Now, one more thing that we have to observe is about this particular quantity. So within this stop band, okay, the maximum gain offered should be minus 40 dB. Okay. okay, or it should be less than or it should be less than minus 40 dB. Okay, so within this stop band, so a stop band will start from 0.21 pi. So here you just try to see at 0.21. Okay, if you see this is the frequencies, so let me take this data tape first. Okay, so if I take this data tape and if you click over here, okay, now I will change this. Okay, so now you just see at 0.21. Okay, the previous point was at 0.208 and the next point is 0.21. So at 0.21, you can find that this gain offered is minus 57 dB. So it is attenuating a lot. Okay. And therefore, we are over meeting the stop band specification. Here we have already got the uh, passband specification, and now we are also over meeting the stop band specification. So it is the best filter. So whatever be the data or whatever be the specification is mentioned in the problem, we have designed a filter which is having better specification. And if we design a better specification filter, then it is allowed. Okay. So because it is over meeting the specification here, right? So now you can see this filter is following all those properties. Okay. Now, suppose if I had taken rectangular window instead of taking this Hanning window, if I had chosen rectangular window, then what will be the result? Okay, so let's just run this code again. Okay, and next time we are going to choose here it is this value 0.19, then 0.21, then this value is 0.01. So if you execute it, okay, it was coming as minus 40 dB. So now let's choose rectangular window. Okay, so here just you have to give this value equals to 1. So if you do that, this m value is coming out to be 90. Okay, so m means it is order of the filter, right? And here is the windows that we have generated. We have generated the rectangular window, and then here is the corresponding ideal low pass linear phase filter impulse response, and then the multiplication of the two. And here in this case, you can see that because it is rectangular window and it is all these sample values are 1. So if you compare, all the samples are similar. Okay, these all magnitudes are same. Okay, so this way we have generated. Now you just try to observe this result. This is more important. Okay, so this result here you can see we are going to get a certain ripple which is very much visible in the pass band. Okay, and now here you can observe one point is that again if you see this cutoff frequency, okay, 0.2. Okay, at 0.2 again this is having its cutoff frequency. And within at this cutoff frequency, this gain should be minus 6 dB. So because this value is 0.201, so therefore it is coming a little bit higher. Otherwise, if you calculate at exactly at 0.2 point, then this value is coming out to be minus 6 dB. Now here you can see if we choose this data types, okay, and if you see what will be the gain offered by the filter when this stop band is reaching. So now it is 0.20 and now 0.208. Now just you see this particular value. Now this is very interesting. So here you can see at this stop band 0.2109, this gain offered within this passband is minus 23 dB. Okay, minus 23 dB. But you see that this gain should have been minus 40 dB. Okay, what we require is at least minus 40 dB. So attenuation required is more. But here, this filter, if we had taken this particular rectangular window, is not able to meet the specification. Here is the problem. Okay, it is not able to attenuate the signal. Here you can just make this comparison, right? So if we choose this frequency response and if we take this frequency response, okay, just to take these two frequency responses together. Now here you can see here the signal is getting attenuated a lot. Okay, at this particular frequency point, it is attenuated a lot, and therefore this gain is minus 57 dB. But here this attenuation is just minus 23 dB. And because this filter, when we are choosing the rectangular window, this filter is not meeting the specification. So I hope you must have understood this discussion. Okay, so now you try to design the linear phase FIR low pass filter by choosing a different specification. So I will stop here now. So if you having any doubt, so you can just put your comments. Okay, I will try to answer your questions. So thank you for watching this video and try to implement this particular experiment using the MATLAB tool. Thank you.